quickly tell you sort of what it's going to be. I guess the organizers, Thiago and I are here, and I guess we start with a pretty small crowd today, and let me still ask sort of who knows how to implement metropolis sampling without help of AI. 1, 2, 3, okay, and then who can write down the Schrödinger equation? Okay, so I guess there's more physics and CS here. But I guess like I'm asking is just because like the subject is going to be like really a mix of these two, very nice ways, and then if you even think about classical Gibbs sampling, there's like very different origins. Like for some people, in more physics, they often thought about the Glauber dynamics. It's like one of the earliest kind of seeds of these Gibbs sampling formalisms. And at the time, it was really only thought about as like a model of thermalization, not really like as an algorithm. But it ends up also becoming an algorithm. And then like the algorithmic origin of this is actually in Los Alamos for the reasons you know. And they use this to simulate neutron diffusion to make something. So it's really a very long time, kind of long history. And then, even today, a lot of the kind of the thing people actually run in computers, like, these diffusion models in machine learning or like simulating annealing to solve optimization problem are kind of Markov chains. So they're very cool. And even today, like TCS, the theoretical computer science community, there's still like everlasting efforts improving mixing time of these Markov chains. Okay. And then sort of more recently, there's like a new toy that physicists and computer scientists have found, which is the quantum computer. So then that kind of somehow motivates a new wave of quantum Gibbs sampling algorithm. So it's this quantum Gibbs sampling. And then like this is actually not a super completely new idea. You can actually kind of see some of this in 1950s, 60s, which is like when people study open quantum system, for a few atoms in quantum optics. So it's really actually physicists have thought about this for very natural reasons. And then you might have heard the Davis generator as sort of one of the things that came out at that time. Okay, and then, well, the issue with this quantum Gibbs algorithm is that we can actually run it. So if we don't actually have a very big quantum computer to do it. So that seems to be a problem, but I would actually argue this is a pretty good time. I would say the golden age for theorists who can use their theory to predict low temperature phenomena for physicists. Before the experiments happen, and then also to just construct new quantum algorithms kind of before it's actually running. Okay, and then for I guess people here are actually maybe more of experts already. But for some of you, that if the formalism appear unfamiliar, it's actually more of a hint that there's new things to be discovered. So we shouldn't be too afraid. And then if you just think about any sort of very classical Markov chain result that you learn from your undergraduate introductory class in Markov chains, a lot of them are just not known in quantum. So that's a pretty, there's really lots of things to be done. Okay. And then so for today, we'll try to be, very friendly, to welcome newcomers, but hopefully this will also be a refreshment for the experts. And so the first speaker is András, who is a notorious figure in quantum algorithm, and he'll just tell us, what are these algorithms, what is Gibbs, this Gibbs sampler. And then just to foreshadow, we will have Thiago and Alex sitting in the back. So Thiago from Berkeley, as you all know him, he's a fast mixer who will tell us about classical and quantum mixing types. Okay. In the afternoon, we'll have the antagonist, Alex from MIT, to tell us about the darker side of Gibbs sampling when mixing slows down. Okay. So yeah, let's begin the day with this András.
Thank you, Anthony. Welcome everyone. I will hopefully set up the stage for this workshop and and explain some of the general constructions, ideas, and concepts behind these Gibbs sampling algorithms. And Anthony already mentioned a bit about the history of these Markov chain Monte Carlo methods, but I thought it's nice to revisit a little bit. Actually, these methods were invented in the late 1940s by Stanislav Ulam, who together with John von Neumann used it to tackle like challenging computational problems related to, for example, the design of the H-bomb. And they were working at Los Alamos, and so the code name Monte Carlo of this secret computational project was actually suggested by their colleague Nicolas Metropolis, who built one of the first classical computers at scale, Maniac 1 and 2. And so this was apparently in a reference to Ulam's uncle, who often gambled there. And so this is the origin of the term Monte Carlo. And the Metropolis algorithm is named after Nicolas Metropolis, who together with Arianna and Marshall Rosenbluth and Augusta and Edward Teller in 1953 developed an algorithm for studying chemical physics problems through thermodynamical averages. And well, apparently Metropolis just built a computer that they run their algorithm on, and it's not super common combination of a husband and wife in a paper. They were all forced to live in Los Alamos in secrecy, so the wife joined the effort, mostly dealing with the programming of this computer for the algorithm. And well, later it turned out that this algorithm is not only useful for these chemical physics problems, and it has turned out to be very useful for studying all kinds of systems with complex degrees of freedom. And there was a generalization to this algorithm by Wilfrid K. Hastings in 1970, who generalized for non-symmetric transitions of the original construction. And it's really a fundamentally important paradigm. In 2000, it was named as one of the top 10 most important algorithms of the 20th century, this classical Metropolis sampling algorithm. Okay, so that's just a brief history of the ideas, and now let's look at the briefly at the core idea behind it. So suppose that we have a regular graph, such as a hypercube, and if you do a simple random walk, then it will converge to the uniform distribution over this hypercube. But what if we want to say we want to sample from a different distribution, say some distribution proportional to 1, 2, 2, 4 on the vertices. So if I have just a hypercube in 2 dimensions, then the symmetric random walk is on the left. It just every time it decides whether it goes left or right with 50-50% probability. Of course, it converges to uniform distribution. And we can modify this walk so that whenever it moves to a less likely position, it accepts that move only with half the probability because it goes to a twice as unlikely place as it was. So the arrows inside that go to the more unlikely positions, they are actually reduced in transitions. And now if transitions are happening according to this new rule set, it's not difficult to see that it actually converges to the desired distribution. And that is due to detailed balance with respect to the station distribution, which is proportional to this like 1, 2, 2, 4 that we wanted. And detailed balance really means that the exchange of probability mass between any 2 nodes is the same in both directions, so the net change is 0. So in the Metropolis algorithm, what you do in general is that when you're moving from a state x to y, then you are accepting this move if you are moving to a more likely position, but only accept the move with the ratio of probabilities if you are moving to a less likely position. And then here in this example, like we have this most likely node. If we are moving from the less likely 2 to this 4, then we accept it. Otherwise, we reduce it with the ratio of the 2 nodes, which is 1/2. So that's why this rule comes out to this in this graph. And so this is detailed balance, that if we make a transition with the modified transition rates, then I am with probably tau x at place x and making transition to y with tau x yx. And then it should be the same as the reverse direction when I'm moving from tau from y, where I reside with tau y and then have the transition probability here. And so this just means that pairwise the exchange is 0. Okay. So more generally, we want to sample from a target distribution, which may be a very complicated distribution. We don't even know how to normalize it, so it can be an unnormalized vector. And so, for example, think about Gibbs sampling from an n-spin easing model, which is a classical easing model now, and it has it assigns some energy to each configuration of the spins according to this easing Hamiltonian, and the Gibbs state is just defined as this exponentiation with a beta prefactor, which is the inverse temperature. So now this is a pretty large distribution. It's over, if I have n spins, that it's 2 to the n configurations, so I have a very large state space. It's hard to know the normalization. But we can nevertheless build this metropolis chain to converge to this stationary state. And so the whole construction is built upon some symmetric exploratory Markov process with some transition matrix T. It has non-negative matrix elements, and we are going to choose, for example, a very simple one where in each step we pick a random spin and flip it, which is basically the random walk on the hypercube. And the metropolis algorithm is first performing a transition according to the exploratory chain, and then, as I told you, it accepts the move when it moves like to a more likely position, and only accepts the move with a probability which is the ratio of the two probabilities, otherwise rejects. And because of detailed balance, this is converges to the right distribution. If you are in this target distribution, then the distribution doesn't change. It's a fixed point. And so now this just describes how to make transitions. And then, well, we need to account for also decay. So when we move away from a position, then we are no longer there. So we just need to extend these transitions with some decay operation, which is basically counting all the moves that move away from a certain position, and that's going to be a diagonal matrix. We subtract that, and now we get this L operator, and we get continuous time dynamics if we exponentiate this operator. That's a continuous time Markov chain, or we can just get a discrete time dynamics. We add identity to it, and then we get a stochastic matrix, and we can iterate t times. So the same rule gives a classical continuous time and a discrete time algorithm as well. The same principle applies. And so Glauber dynamics is very similar, just it has a different acceptance probability. And it turns out that we can just choose any sort of accept-reject function which satisfies this detailed balance condition that if I'm moving to, I'm making a move with ratio R, then the acceptance probability should be R times the acceptance probability of doing the reverse move. And so this in general works. And in metropolis algorithm, one particular function satisfying this detailed balance condition is this metropolis function, which is maximum of 1 and R. So if we move to a more likely position, accept, otherwise only with the ratio. And Glauber is this more smooth version of this metropolis rule. Both of them satisfy this fundamental equation above. And this is really just a simple proof. You had your symmetric transitions, and then you are reweighing the transitions according to this function. And you want this to be detailed balanced, which is just this equation that moving from one to the other place is same as moving from other to the previous one, weighing. And if you just rearrange, then you get that indeed it is going to be detailed balanced if and only if you have this functional equation satisfied. Anyway, so like you have a large family of these acceptance functions, and metropolis and Glauber are just same principle but with a slightly different function in the accept reject. And again, the key is that we can ensure that the probability mass exchange is equal between any pairs of the nodes. And so this is a very classical way of thinking about it. We think about pairs of states and transitions between them. And a more useful way in the quantum case, where it's less easy to establish what is exactly the nodes of the graph and so on, because everything is superposition, is to look at this detailed balance condition in an operational way. So if I look at this transition matrix, T prime, which is detailed balance, then basically this means that if I multiply with the diagonal matrix with the target distribution, this is the same as if I multiply with this diagonal matrix the transpose of this transition matrix from the left. That's exactly the same. That's a matrix form of expressing these pairwise exchanges that I told you before. And now you have this matrix equation. You can just make it more symmetric by multiplying both sides with the square root tau inverse, and then you get the same equation here. And now it says something different, that you have a matrix, which is the transition matrix. You're multiplying from left and right with square root tau and its inverse. And now this is actually a self-adjoint matrix according to this equation. So now detailed balance condition can be expressed as a symmetry of a certain Rivet transition matrix. So this transition matrix is detailed balance if and only if this Rivet version with square roots is actually a symmetric matrix. And now this is a more operational form, and this is the form that we will use for generalizing to quantum detailed balance, because this doesn't rely on specific states, and it's a more fitting language for the quantum setting. Okay, so now let's move to quantum Markov chains. Quantum Markov chains or quantum channels, these are just completely positive and trace-preserving operations in quantum information, and so they can be written in this form. And this form on the left, it just is the form of completely positive maps in general, and it's trace-preserving. That means that if you are adding the reverse order product of these Krauss operators, and then they add up to the identity. So T-dagger identity, that is just the same as this sum here, should be identity, and that means it's a trace-preserving map and completely positive by the structure of this form. Okay, so that's a quantum channel. And the continuous time version is sometimes more convenient to work with. And so then we need to understand these continuous time quantum Markov chains or quantum dynamical semigroups. And that's exponentiation of a so-called Lindbladian. That is the infinitesimal generator of these groups. And so they have a similar form to quantum channels. They have a completely positive map. And they have this so-called decay term where it basically, these transitions are like the stochastic transitions in a Markov chain. You are moving to another position, and because you moved away, then you are no longer where you were before. Then you have to account for that, and that's the decay term here. And because it's quantum mechanics, you have additional freedom. You can actually add some coherent evolution to the picture. If you would have no stochastic jumps like this, just have this coherent term, that's actually the Schrödinger equation, just in the language of density operators, which is called the von Neumann equation. So if you would only have this coherent term, that would be just basically Schrödinger evolution. But now you can combine stochastic and Schrödinger in a single picture, and that is quantum Markov dynamical semigroups. And I will look at this a bit more abstractly, that I have some transition part, which is describing transitions. I have a necessary decay term, which is accounting for trace preservation. And then I have a coherent term, which is the extra freedom in quantum mechanics. And so now what is detailed balance? I told you that the transition operator should be reweighed by the stationary state, and then that should be symmetric. Now that's everything is with complex numbers here, so it will just mean that it's self-adjoint. And because it's quantum mechanics, well, it's unclear where to put this square root of rho. If you multiply these powers of rho, it's a square root. Yes?
Sorry, can you explain again in what way this decay term accounts for, you said phase preservation?
No, sorry, the decay term is trace preservation.
Trace preservation.
So yeah, because yeah, if we wouldn't add this, then basically all the jumps just would add up my existing state, and my state would grow. And this ensures that the trace is preserved because I'm just removing place that has been moved by a jump. Yeah. So that is the same as, well, basically, if I would go here, I have the transitions here, and this is not a Markov chain yet because the transitions from a single vertex is now only like 3/4. And with 1/4 probability, well, I just remain there. And that's basically, I need to like add these diagonal terms, which is just, I'm summing up when I removed and normalize with that. And this is exactly this diagonal entries summing up all the moving away jumps. That's exactly the analog of the quantum decay term.
But here it's on the level of the transition matrix directly.
Yes.
And so, the Lindbladian, so the exponent.
So yeah, these transitions, you can use them in a continuous time fashion, like here.
Ah, great.
So continuous time dynamics is exponential TL, where TL is these transitions minus decay. That's exactly the Lindbladian analog. And in the classical case, you can also just add an identity to it, and this was like all column was 0 in L. Now all column sums to 1. That's now a stochastic matrix. In the quantum case, it's a bit more complicated. You cannot add identity to the Lindbladian. That's not going to be a quantum channel, but at least the continuous time setting is very similar.
Great, thanks.
Yeah. Okay, so back to detailed balance. So I need to reweigh by somehow square root of the target row inside and outside, and that should be self-adjoint. And well, the most nice way is to arrange this reweighing by square root of row by splitting it half, reweighing from left and right with square root, like fourth root of row, and the same on the outside. And this turns out to be like the most general generalization of the classical detailed balance conditions. So we say that this transition matrix is detailed balance with respect to my density operator rho if this is a self-adjoint operator. And now think about rho as some Gibbs state, some e to the minus beta h for some Hamiltonian. That is without loss of generality. Every quantum state can be written in that form, which is of full rank. We'll assume that we have quantum states which kind of cover the whole space. And so it turns out that the Lindbladian is detailed balanced if and only if the transition part is detailed balanced, plus the coherent term has this very specific form. The coherent term is completely described by the decay part, so this T inverse identity summa decay. And the coherent term has to be this functionally related to the decay term. So these psi I and psi j, they are just eigenvectors of my Hamiltonian and therefore eigenvectors of my density matrix. And EI, EJ are just the energies correspondingly. And so it just says that if you have some psi I, psi j matrix element in the eigenbasis of your Hamiltonian, then it should be weighed by this 10h of the energy difference times beta over 4. This just has to be it. This has been known that this form is general, but this simpler expression in terms of, relatively simple expression in terms of the energies is what we discovered with Anthony and Michael in our paper. So anyway, the key message here is that the transitions have to be detailed balanced, and that would have been enough in the classical case, but now non-commutative phenomenon happens, and this decay term can actually ruin detailed balance. The problem is that if the decay term doesn't commute with your density operator, which is your target, then this non-commutativity can break detailed balance. And if it happens, then you can always fix it with an appropriate coherent term, and there is only one coherent term that fixes it. And all detailed balanced Lindbladian is of this form. The transitions have to be detailed balanced, and then if the decay would happen to break detailed balance, then there is a unique coherent term that fixes it. So that is the structure theorem for this KMS detailed balanced superoperator, Lindbladians, and there are more restrictive versions of detailed balance, but I don't want to go into that in this talk too much. Okay, so why is this detail balance important? Why we like it? So in classical detail balance, this was this probability max exchange, and that ensured that fixed point is correct, and it was equivalent to this symmetry of this rebate transition matrix. And in the quantum case of a completely positive map, we have this analogous rebaying of the transitions, but in the quantum sense, and this has to be self-adjoint. And similarly to the classical case, detail balance ensures that this target distribution is indeed the fixed point. My Lindbladian dynamics will converge to it, and it's just using this self-adjoint property, it's very easy to like show. This L-Dagger identity is 0, that's just trace preservation in the language of Lindbladians, and I just use this detail balance property, and I get that indeed it's a fixed point. It's a very simple one-line computation. Yes?
Comment very briefly, perhaps, what happens when the Hamiltonian is commuting? Like, is the point that this T operator unidentity, it's diagonal, perhaps, so you don't get this coherent term? What happens?
Yes, indeed. So basically that's the case. The coherent term that is described by this equation says that if your decay commutes, then the coherent term is 0. And indeed, if you have commuting Hamiltonians, then typically the constructions that you get, the transitions are not just detail balance, but the decay is actually going to be diagonal in the Hamiltonian basis, and you don't get this. So this is a new phenomenon that is typically tied to non-commuting Hamiltonians.
Yeah, I guess because in the commuting case, K would be exactly, you would actually know what energy has changed. So if you do the dagger, you actually just put it back.
The reason this is tricky is because it might be a degenerate.
But energy hasn't changed, so.
Yeah, so somehow, if you have this more restrictive form of detail balance called the GNS detail balance, then that ensures that you are only jumping between like fixed energies in a jump, fixed energy difference, and that means that your decay associated to it has to be diagonal in the eigenbasis of the Hamiltonian. So yeah, GNS has this. Yes?
You just said that if the Hamiltonian is commuting, it's clear from that equation that the coherent term is 0. Is that?
It's not clear. That's you have to have a bit of background to like see. Yeah, basically, it's not at all. Yeah, it's like, you know, if you like go to the literature and you want to reprove it, it's probably several pages of proofs to like get to this. But yeah, like from the structure theorems of this like more restrictive detail balance and so on, it's clear, but you need to know the structures and so on.
Actually, how does that even? Because I'm just that equation only has the spectrum, right? Like the only data about the Hamiltonian that shows up in that bottom equation is the
Yes.
values. Like, how does it even know whether the terms are commuting with each other or not?
Okay. Yeah. So it's more like the transition operators that you naturally write down for commuting operators are such that this is going to. So like for commuting Hamiltonians, the transitions that you come up will naturally have this, but it's a more circuitous route. So it's like you are right that just from this equation it's not apparent.
If you want, you can write down this Gibbs sampler for a commuting and has a coherent term if you want. But like, yeah, but it ends up being like the most natural one where they have no coherent.
I see.
Yeah.
Okay, maybe a related question is it like if you, I guess the diagonal case, like when H is diagonal, that's like we're talking about a classical probability distribution. Like rho is a distribution. Is it still interesting to consider like quantum markup chains to converge this classical distribution that do like uniquely quantum things inside the top?
Well, we didn't find. In principle, there could be something there, but we didn't. But it's not that. Yeah, like it doesn't naturally show up. So, and indeed, like Alex will talk about, is that if you have a classical system, then your classical problems also apply to the natural class of quantum algorithms. So, it doesn't seem like certain problems you can't fix by just going quantum, and it's unclear if there is like natural kind of issue that you can like do better quantum way for classical systems. So we don't really have good examples for that. But I imagine that you can come up with something like, I don't know, some quantum tunneling put into quantum Markov chain. I don't know, something like this, probably possible, but don't really know any like compelling example. No.
I see.
Yeah. Okay, so detail balance ensures the fixed point, and that's a major relief because these super operators can be like quite unwieldy to handle, and at least we know that the fixed point is correct, which is very hard to argue otherwise about. So this detail balance, without detail balance, it's very difficult to show that you are converging to the right state. And so the story of quantum generalizations of this metropolis algorithm is deeply tied to how you handle ambiguity in learning energies or phase estimation. And then, so the first attempts tried to somehow just force it to be basically they tried to convert a quantum system to like a diagonal operator and then treat it as a classical Markov chain. So it was kind of the opposite direction as what you asked for, like, okay, what if I do have a classical system and want to treat it quantum? Now it was opposite. I have a quantum system, I try to treat it as classical system in the eigenbasis. But then moving to the eigenbasis is difficult. You cannot really estimate energies, and it was problematic. And there was like a series of works that tried to like get better and better at handling this issue, and progress was made, eventually resolving these issues. And now it seems that just a few years ago, we arrived at a convenient version that handles this ambiguity in a nice way. And so there have been some approximate versions. So it's like a large sequence of works that tried to improve but wasn't fully satisfactory. And basically 2 years ago, with Anthony and Michael, we built on the previous ideas and found a version which basically solved this issue by somehow not requiring phase estimation to too high precision, not even attempting to argue that it's like infinite precision or approaching that, but just accepting that we are limited in how much we can learn about the energy spectrum and the eigenvalues. And that was some damped phase estimation, and operator Fourier transform is the technical ingredient behind. And that finally gave a quasi-local and detailed balance map. So what it means that in original metropolis algorithm, you only depend on energy differences. So if you do a local change, then you only have to look at your neighboring configuration and then decide whether you accept a jump or reject. And so every update is local. Now, unfortunately, for non-commuting quantum systems, this cannot be done. Commuting quantum system is fine, but non-commuting one, you kind of depend on a larger neighborhood. But still, because you are estimating only energy differences, that's a quasi-local quantity. And so your jumps will be approximately local and exponentially close to a local operator, basically. Yet you can still have detailed balance. And basically, we are shuffling the energy uncertainty and ensure that it's Gaussian. And if it's a Gaussian uncertainty, we can cancel this out magically. And that's one of the key ideas. And an even more fresh development is that, well, maybe you don't even need to estimate energies at all. Just somehow do some clever reweighing of your jumps. And this can be done, although this looks weird thing to apply a function to certain jumps based on how much energy they change. But it turns out that you can express this rule as a weighted integral of a Heisenberg evolution, so something physically related. And I will talk a little bit more about this. But I just wanted to say that the story of quantum metropolis algorithm is how you handle ambiguity in estimating phases. And we basically went from just, okay, estimate it exactly, basically turning it to a classical problem, Gibbs sampling, to all the way around to don't even attempt to estimate it. That's the latest development. Like the first really nice resolution was then, okay, accept that there is Gaussian uncertainty and just juggle this uncertainty. And now the latest version, don't even attempt to learn energy differences, just somehow manipulate the jumps in a coherent fashion. So the story is basically, you don't need to learn energies at all, and that makes your life much easier. I will talk a bit more about this. Okay, so basically I described you that having a detailed balanced Lindbladian basically means that we have to have a detailed balanced transitions, and then everything is set by that. And how we achieve that? Well, the constructions that we have are linear, and at the space of superoperators, these transitions, these exploratory quantum Markov chains. And that's nice because we can just analyze them at the level of Krauss operators, which we couldn't do for nonlinear transformations. And the early attempts and the classic and this open system theory in some infinite time limits leads to the Davis metropolis generator, which is basically, okay, it's not exact what I'm saying, but more or less something like this. That you are just doing classical metropolis in the eigenbasis of your Hamiltonian. But this is discontinuous in the Hamiltonian because what is the eigenbasis that can change when energies cross and so on. And so this is really not physical in a sense in finite time regimes. And so one solution is making this operator Fourier transform and Gaussian damping to estimate energy differences with the Gaussian uncertainty. And so what would happen here is that suppose that K is your jump operator, that's one of the Krauss operators in your exploratory Markov chain, and then you are trying to estimate how much this changes the energy. And this Heisenberg evolution turns out to exactly diagnose that. So K omega is the part of K that induces transitions roughly omega up to Gaussian uncertainty. And then you just do these jumps according to this. So basically, each jump is performed here, and you learn this label omega. So this is now a new Krauss operator in your representation. That means that when this jump happens, you learn about your system that roughly omega energy change happened, and you are reweighing it with the metropolis weight. And actually, it turns out that to account for uncertainty, it is sufficient to shift your metropolis rule by a fixed amount, which is related to how much uncertainty you have in energy estimation. Like how wide is this Gaussian estimation that you got. And it doesn't only hold for the metropolis rule, any kind of classically detailed balance rule that you had, like Glauber and so on. If you just add the shift to your energy estimate that you have seen, it will just magically cancel out the uncertainty in energy that you suffer. And generally, you need, in order to not annihilate jumps too much, you need energy uncertainty at most 1 over beta. So that's how fine you need to resolve your energies. And
the shift always the same?
So the shift depends on the uncertainty in energy estimation. And so, yeah, when beta is 1, it's by, yeah. It should be tuned according to the uncertainty, but a convenient choice is 1. I just wrote there because that's our recommendation.
But it doesn't depend on that.
No, it only depends on how wide is your Gaussian uncertainty, the standard deviation of that, yeah. Okay, and it turns out that this has been known in the classical case, but it's not immediate that it can be imported to the quantum setting, but that's hard work Anthony did for us, and we know that it works now, and then people generalize it further. And the coherent reweighing says that, okay, look at your jump operators. Oh, sorry, yeah, on the right-hand side there should be no row. So K was your original exploratory jump, the self-adjoint jumps. And then K row is the new one, which is now detailed balanced, constructed to be detailed balanced. So what it says that you look at transitions between eigenstates and look how much they change energy. And according to that, just reweigh the transitions, and that is going to be So the matrix element in the eigenbasis of the Hamiltonian should be reweighed by this function, this determinant function, and you put there your energy differences, appropriate coefficients. And that's the rule. And now, the nice thing about this is that if you had a single Krauss operator, that gets mapped to a new single Krauss operator, and somehow the Krauss operators correspond to individual jumps, and this means that you don't learn any information about the energy change because the Krauss operator's name doesn't reveal the energy change that happened. Unlike in this case where Krauss operators get labeled by energy differences. And there is a question.
So I think it's something basic. So is the claim for these two equations here that like you start with any channel given by Krauss operators k, and then you apply the transformations in here, the resulting object will be detailed balanced for the Gibbs state for H.
Exactly, that's the claim. You have to start with a self-adjoint transition, superoperators, and then similar to the classical case where we have started with like a symmetric transitions and then Metropolis work. And yeah, in classical case, there is this Metropolis-Hastings algorithm, which doesn't require symmetric transitions to begin with, but it doesn't really have a nice quantum analog. We didn't find. We found quantum analogs of that, but they are not nice. So basically, just start with a self-adjoint exploratory quantum Markov chain. For example, if you just look at this, pick a spin randomly and then apply some Pauli X or Z or Y, that will be always self-adjoint because the jumps are self-adjoint themselves. Yeah, and then these are two different constructions, and both of them ensure very different because one preserves the number of Krauss operators, one even from a single Krauss operator can create a gazillion of jump operators, but both of them ensure that the new map is going to be detail balanced with respect to your target row. And okay, so as I told you that moving in the eigenbasis and then doing this reweighing, it seems like a daunting task because we don't know the eigenbasis of the Hamiltonian. But this like matrix element-wise transcription, which is here, actually can be expressed as just some integral over Heisenberg evolution of your jump. And now this is nice because you just need to do Hamiltonian simulation, and this is basically, this integral can be approximated by linear combination of these terms. So basically what ends up happening on a quantum computer that you just prepare some superposition over f's, over times, which is like proportional to the ft. And then you do, by this time register, you do this Heisenberg evolution, and then this circuit just basically gives you this approximate integral, and then you have your new jump. And the precision scaling is very nice because these are smooth functions, and then that it means that to get an epsilon precise approximation of your jump operator, you only need like log 1 over epsilon resources.
So it's maybe another basic question. Is there some like condition that like this K you start with has to, I don't know, be like fully connected or something? Like if I imagine just taking the identity channel, like on cross operator's identity, then surely that's not going to give rise to a...
Yeah, so yeah, that is related to the question of uniqueness. So indeed, if your exploratory Markov chain was that its unique fixed point was, so if it's self-adjoint jumps, it means that the fixed point is the maximally mixed state. And so if the maximally mixed state is the unique fixed point, and you apply the first construction, then the Gibbs state will remain the unique fixed point. For this other construction, there might be some pathological counterexamples, but still generically this is true. Like, but apart from a measure zero stat, it holds. But maybe there is some like very pathological example because it doesn't.
I think the identity channel is detail back.
Wait, it's what?
I think the identity channel is detail back.
Yes.
Oh.
It's not very useful, but.
So, yes. Why do you say
But
this?
it's still consistent.
That's true. But like if you plug it into this equation and get like a K omega, will that thing also be detailed? I guess it is, right? Because it's the theorem.
Is it? I think it would just be sort of proportional to identity.
I don't understand what's the question. So there may be multiple fixed points, but yeah, But then when the original process had a unique fixed point, then it's most likely preserved by these constructions. That's yes?
Can you explain what the coherent reweighting is? The equation doesn't quite make sense to me.
Yeah, okay, so there is an error in this equation. This row shouldn't be here. This row is a mistake. This row on the right-hand side, do you see my mouse?
Oh, yes.
This shouldn't be there. That's a typo. So K is the original jump operator of your self-adjoint transitions. And now you get a new transition matrix. It's a new Krauss operator that is a derivative of this original Krauss operator. And the matrix elements are defined by this formula. These are eigenvectors of the Hamiltonian and corresponding energies. So it tells you that I had a self-adjoint jump. I do modify the matrix elements according to this formula in the eigenvalues of Hamiltonian, and I get a new Krauss operator. And this new Krauss operator will give rise to a detailed balanced channel with respect to rho, where rho is e to the minus beta h.
And it is not guaranteed that the K superscript rho remains local as K was?
Well, yeah, in general it will not remain local, but because of this integral representation, you can see that it remains quasi-local. So if K was a local one, then because of Lieb-Robinson bounds, this Heisenberg evolution remains quasi-local, and it's, well, this F is actually a rapidly decaying function in our applications. And so basically, you can truncate around beta, it turns out. And so it will be like the local operators, locality increases by roughly beta. It remains quasi-local with a radius up to beta after that. And that is a consequence of this integral representation. So yeah, this integral representation is useful for 2 points. It ensures that quasi-locality is preserved, and it also gives an efficient implementation of these new channel operators. Okay, and yeah, so one story of this, I told you that what do we learn, or the environment learns when a jump is performed. In Davis, it learns the energy differences exactly. That's why it's unphysical. With the phase estimation with Metropolis, it approximates energies before and after. This operator fully transform only approximate energy differences, and the coherent reweighting, the newest one, that actually learns nothing about energies. So this is the story of learning less about energies makes you better algorithms, basically. And an important consequence of this detailed balance condition, that you get a so-called, we call it a parent Hamiltonian of your Gibbs state. So once again, we have a detailed balanced Lindbladian of this generic form. And if we group together the decay and coherent terms in this simple fashion, then we can construct a parent Hamiltonian. So now this di is just really ki dagger k. So this is the decay corresponding to the ith term. This is the ith term of the Lindbladian. And so you get these 3 terms coming from a single Krauss operator. And now this is in a Hilbert space of double the size. So this star just means that conjugate every matrix elements. And so it turns out that if you look at this parent Hamiltonian, this will be a Hamiltonian whose ground state is the purified Gibbs state. So this is the eigenbasis of your Hamiltonian. You again duplicating it with complex conjugation. And so this state turns out to be a purification of the Gibbs state. And this pure state is a ground state of this parent Hamiltonian that you got from your detailed balance quantum channel or Lindbladian. And so whenever the fixed point is unique, so your Lindbladian actually converges to the Gibbs state, then for this parent Hamiltonian, the purified Gibbs state will be the unique ground state. And because every term individually actually is detailed balanced by the construction, it means that you get a frustration-free quasi-local Hamiltonian of the purified Gibbs state. So a detailed balanced Lindbladian actually translates to a parent Hamiltonian which is frustration-free and quasi-local, and it's parent Hamiltonian of the purified Gibbs state. And this is very nice because now you can just work with this parent Hamiltonian and devise algorithms based on adiabatic schedules and so on, which actually prepares the purification of your Gibbs state, which is a much more strong resource than just having the mixed state as a Gibbs state. So it actually unlocks much richer algorithmic tools, and also it connects to the theory, to the well-established and rich theory of frustration-free quasi-local Hamiltonians. You can just import all tools and results from there and like translate them to results about the Gibbs state through this parent Hamiltonian.
Can you say something about where quasi-locality comes from?
Quasi-locality is coming from, say, this integral representation. So f is a rapidly decaying function. After roughly beta, it decays exponentially. So yeah, assuming that you had like local Krauss operators to begin with and you apply this construction, then this will be a quasi-local Hamiltonian that you end up with. All right.
The locality is exponential in beta.
No, it's linear. Linear in beta. Because yeah, beta is like how long you need to do the Heisenberg evolution, and then Liebowitz bounds tell you that if you do time t Heisenberg evolution, then you spread roughly time like t, the locality. Okay, well, I guess I already told you that with LCU you can implement it, and well, I don't have too much time to talk about this, but Lindbladian simulation can be a bit complicated, so we also devised, we moved back from Lindbladians to discrete time quantum channels, and that's one way to do it is just do Lindbladian simulation for a fixed time t, but that's quite complicated, and now we devised also discrete time versions of the algorithm, very explicitly telling you what is the complementary Krauss operator you have to add to get a proper detailed balanced quantum channel. And it's much more complicated in the classical case when we just added identity to these like jump operators and we got a Markov chain matrix. Now that wouldn't work here. You have to work much harder, but it's possible. And actually, this also is a quasi-local construction, and we have explicit formulas and Taylor series and everything. So we analyzed it well, but unfortunately more complicated. But still, we believe it's a good contender for actually applications if you want this detailed balance map exactly in a quantum computer, then this might be a good way to do it. And okay, so here is just a summary of these different constructions, of known constructions, and I am focusing here on the versions that satisfy detailed balance exactly, and there are many others which are only approximate detailed balanced, and the growing number of these. Probably if you want to run something on your quantum computer not too far term, you want to do things approximately, and then you can cut some corners and have much simpler operators on your quantum computer. But for the purposes of this talk, I just want to describe exact detailed balance because that's the nicest from a theorist perspective, and see what we have there. So in the classical case, Glauber and Metropolis, these are very efficient to implement. They are actually exactly local. Locality increases by just the range of the interactions in Hamiltonian, and they have zero energy uncertainty. It's classical system, you know everything, and ergodicity preserving, by which I mean that if your exploratory process had a unique fixed point, then the unique fixed point will be the target distribution. And well, there's this Krauss rank, which is like how much more complicated jumps become. They don't become more complicated, basically, in the classical case. And now I can contrast this with the Davis generator. We don't know how to implement it efficiently, and it's basically impossible in general. The jumps will become completely global, which is the consequence of the zero energy uncertainty that it requires. It's ergodicity preserving and can blow up horribly the complexity of the map. Many more jumps can appear. Now, phase estimation based, when done with Gaussian damping, actually it's efficiently implementable. It's also not going to be local because it learns energies before and after jumps, but can deal with finite amount of energy uncertainty, once again preserving fixed point, but can do many more jump operators. And similarly, other constructions like this only energy difference learning operator free transform and its derivatives behave similarly, and the new ingredient in them that they are actually quasi-local. So now, because we don't attempt to learn energies before and after jumps, which is learning global quantities, we only learn energy differences, which is a quasi-local quantity. The entire algorithm and the jump operators remain quasi-local. And then we can push it to the extreme with these coherent reweighing schemes, which actually don't learn anything about the energy, yet produce quasi-local operators, and they don't even blow up the Krauss rank. So this is the story of how learning less about energies give you nicer algorithms in a way. Yes?
Sorry, what does it mean to ergodicity preserver?
Yeah, it means that, so the story as I told here is that you have a self-adjoint quantum Markov chain, a self-adjoint quantum channel, which I called exploratory quantum channel. And we start with that, and we make it detail balanced by the construction. And so if the exploratory Markov chain had the maximally mixed state as the unique fixed point, then the modified version will also have a unique fixed point, and it will be the Gibbs state. So the constructions on the left preserve the ergodicity of the quantum Markov chain of Lindbladian.
And what does almost surely mean?
Well, that if on the set of self-adjoint jump operators, there is a zero measure stat where it breaks down. Yeah, so basically it can only break down in accidental cases. Okay, and well, open questions and recent developments. So a big open question is like, in which physical systems can we expect fast convergence of these derived Markov chains, quantum Markov chains and Lindbladians? And we know that for high temperature lattice Hamiltonians, actually these constructions are rapidly mixing, which is the best thing that you can hope for. It was proven by Rosé, Stiltfrank, and Alhambra last year. Random or sparse Hamiltonians at fixed temperature are also mixing fast. And similarly, related result is that Hamiltonians that satisfy the eigenstate thermalization hypothesis, they also thermalize in a quick way. And this was proven by Anthony, Fernando, and Oleg and Ramis. And the latter is some near-term tailored approach. But these are somewhat approximate, so that I didn't mention the explicitly here. And the more recent results from this year is that free fermion models and slight perturbation of those is actually also fast mixing. And by two groups show this independently in January. And there are also promising simulation results for one-dimension and quantum chemistry systems, which was proven by a group involving Li, Zhan, and Lin. And on the dark side of the things, we will hear about this, that there are also bottlenecks in the landscape that can cause slow mixing, and similar to the classical case, and even the quantumness doesn't seem to help those bottlenecks at all. This was also proven by two independent group of people recently. We will hear more about this in the last talk. And so there are some general open questions that haven't been analyzed that much. For example, how noise resilient are these algorithms? They are somehow doing stochastic jumps and randomness in the process. So it's reasonable to assume that if there is some error in the implementation, that noise will also dissolve slowly. But how slowly and how much robust these are, that remains to be seen. And then ground state preparation versions have been developed championed by Lin and his co-authors. And there it's a bit more difficult because detailed balance is not well defined, but they developed recently some tools to, despite this, provide new methods for mixing times, but there is still a long way ahead for these algorithms. And another interesting problem is how we get the secondary type quality gap amplification in these methods. So it's known that if you have a classical Markov chain which is detailed balanced, then you can convert it to a quantum walk algorithm, which basically quadratically magnifies the gap. So it would be natural if you start with an incoherent Lindbladian or quantum channel, maybe can you somehow purify it and magnify the gap quadratically. And this is only known for constructions with approximate detailed balance, and we don't know how to achieve this gap amplification for the more appealing and exact algorithms that we have developed. For some technical reasons, it's just not known how to do that. So that's also a compelling open question. And well, with this, I would open the stage for questions. Thank you.
Any questions?
Oh, okay. One question is, I guess, is there like a relation between like these algorithms and like the actual physical process of thermalization? Because I guess it seemed kind of striking that like there's still, from your table, there was no algorithm for the quantum case that actually had like strictly local dynamics. But like we do expect that in like reality, like local dynamics will, like, you can couple a system with like a bath with some local dynamics that it will thermalize, right? Like it's
Well, okay, so yeah, this is a very good question. So first, yeah, we have been talking about this with Anthony, and there is also some paper that came out recently which finally gives a KMS detailed balanced Markov, this quantum Markov chain derivation, which is very much physically motivated. And well, there is some slight trace of some coherent evolution remaining there, which is basically means that you have a slightly disturbed version of detail balance that you can satisfy. There is some coherent term remaining that commutes with the Hamiltonian operator itself, and so it will be not detail balance in this cleanest form, but a related version which is still ensuring the fixed point correctness can be ensured, but adds a bit more complication. But this, this derivation, which is actually detailed balanced Lindbladian for first principles, that it just happened a few months ago. So there is work in bridging the gap, and the construction is related to the things that I told you here, but has some slight differences also coming from this physical origin, but is in the same ballpark of constructions. But yeah, this important difference is this remainder of this coherent term there. And regarding locality, I think that this quasi-locality actually also arises in this physical derivation, and that happens because there is this back and forth interaction somehow with the system environment. That's inevitable, and well, or maybe that's not the best way to put it. Maybe it's a bit misleading. But anyway, so somehow when you have non-commuting Hamiltonians, then these jumps that arise naturally from this picture, they do have some non-locality, because just the spectrum of the Hamiltonian is like that, and that seems unavoidable. I don't think anyone proved that there is no local dynamics, but I expect that to be the case. I don't know if you have.
I don't know. I think currently all the only like strictly local dynamics are for commuting. Yeah. And I guess to add like one reason that you get, I guess usually when people do like this error correction, they think the noise is like depolarizing, right? It's kind of localized. But then like whenever there's Hamiltonian term that's like rotating, it actually just force it to have a tail. Because like their system has its own Hamiltonian that's like evolving, and that somehow is causing this issue. It's also like fundamental because like if you don't know the Hamiltonian, how are we going to cool it? Like so like it is somehow when your bath is trying to interact with the system, you want to learn the energy. You know, should I heat or cool? It actually needs to evolve Hamiltonian a little bit, and that somehow makes it non-local.
So it's about the fact that you have to learn about the system. Is that maybe a way to put it?
Yeah, somewhat. I mean, the bath has to do. The bath needs to know what they want to accelerate.
But if I just run the Hamiltonian, it will thermalize, and it's all.
Right, but then energy will be preserved. So like the bath somehow needs to know whether I want to take energy out of or put more in. Yeah.
I thought that was equilibration, but it sort of automatically knows.
Right. If it's closed system, then the energy would kind of mix within its site. But then if the bath, the bath has a temperature, then it would want to like, want to force. If the system is too hot, it has to take energy out. Yeah. So physically, I think it's necessary to just you have to somehow evolve.
So you're saying if a physical system that I couple to a bath is local, it won't thermalize?
So like, okay, like somehow the coupling should be understood as this original Markov chain, these original K operators, they can be local. But somehow how these jumps are interacting with the bath and the system, that interaction makes these local jumps quasi-local. And that is somehow through the interaction with like energies and
because you want to simulate that interaction, you need the quasi-local.
Does the quasi-locality involve inverse temperature parameter?
Yes.
So I guess that's the issue. Why does it have to know as you always have to know bigger and bigger subsystem as the
I think there's lower bounds for this. So you actually do. I think there is lower bound for this. Like, in order to like, I think even to prepare reflection for the purified Gibbs, so you somehow need to access the Hamiltonian for at least some time. Because the Gibbs is like some kind of there's like some function, and then it's become more and more like steep when beta gets very large.
But just to be clear, like we're just talking about like whether the thing is like none of the algorithms here have like a time guarantee. Like, it's just like a stationary state, like the Gibbs state.
Right.
So like, I don't know. It just feels weird that like we have a lower bound that just to like hit the Gibbs state at all. Or, like,
yeah. So I don't think. Yeah. So as I told you, I don't think there is like end-to-end proof that there is like no local. In general, there is no local invariant doing this job, but all the ways we know how to do it, like all the ingredients suggest, and it's like individual ingredients we have lower bounds, not in like this ultimate statement. But yeah, the intuition that we build up is that this lower bound should probably hold, but there is no proof, so maybe we didn't see some opportunity there. Yeah.
But like this beta scale actually shows up in many places. I think in a lot of Hastings has this belief propagation. I think they also have a beta scale. Anyway, so this beta time scale actually shows up in other places too.
Yeah, as a time scale, I understand it, but not as a locality scale.
But time becomes locality,
Why?
If you evolve it with, if you do like Heisenberg dynamic, then time becomes space.
And you need to do the Heisenberg dynamics for it.
All the way we know
Okay.
Any more questions? I guess we can have one more question or. Okay, so if not, thanks András.